Yeah. So this is this talk is about an index data structure, and this work was published on EuroSys 19. It's a new like faster ordered key value index. So I'm going to start with oh sorry. Okay, there are some slack between the switching. So a few words.
Xingbo, actually, before you even go, I have a thing that I want to ask on the title itself.
Yes.
So when you have data in memory, why do you need ordering within data in memory?
So the ordering is mainly for accessing data in order. Like the range queries in databases is kind of very important in some scenarios. Like you want to search the data between like two keys, A and C. You want to find all the keys like started with like a prefix B. All those kinds of queries requires an order index so that the keys are like clustered together according to their alphabetic order.
Okay.
So yeah. So in contrast to ordered index, another main theme is about hash table. I'm going to talk about this in the first slide.
Okay, sure. Go ahead.
Yeah. So so there are many terms for the databases on the market, and you must have heard of like document database, graph database, and column stores. A lot of names. If you go to the NoSQL database.org, you will find a lot of different names and maybe thousands of key value stores there. But today, when we are talking about these indexes, I try to like simplify the landscape of the key value store, not key value stores, the databases in general. So we all know that the old ones, the SQL databases, they have been there for 40 or even maybe 50 years. They are used to store data in tables, and the tables are organized as columns. They have very strict definition of how to manage the data, and there are like thousands of different kind of queries you can express using the SQL language. Those systems are like very complicated, and the design of them are not based on a simple model. And usually in those systems, we observe a very low, relatively low access speed, such as 1,000 to maybe 100,000 operations per second. Those systems usually needs to do a lot of sorting, indexing on the query time, and also involves a lot of I/O. That is the main problem. So now people are looking more at NoSQL databases. The NoSQL does not mean that we are totally abandoning everything from the SQL databases. Instead, we are looking at different ways, like for particular optimizations for the databases. For example, if your database only requires point query, then you never need to like look at keys in a range. You may actually use a hash table-based database that can quickly find your keys with less CPU cycles and I/O. But in general, the popular NoSQL databases, such as those like LMDB and LevelDB, they are kind of key value stores. Like the key value stores are the most simplified model for NoSQL databases. They just use keys and values in the system, and those systems, those key value stores, they need to use an ordered index so that we can achieve like most simplified range queries on the data set. Because if you just use hash tables, like the functionalities of the database will be limited. Like you can only do point query on those data. So they need to use ordered indexes in the NoSQL databases, or most of the NoSQL databases. And there has been another kind of, it's not even a database, it's kind of a service. And if you have done web development, I think you have heard of memcached. And those work I listed here, like memc3 and Mecha, they are like improvements to the memcached or or similarly, I think there's another popular key value store, key value cache for the Redis. So those key value caches, they serve a very specific purpose. That is, they want to accelerate the access to some very hard keys. Like you frequently access those keys in a high frequency, and you also want to keep those things updated. So like every time when you have an update to a key in a key value cache, you want to get the updated results immediately without like waiting for it to going into the disk and get sorted in the database systems, right? So in the key value cache, they usually just use a hash table based index. That means in the key value cache, we don't have the capability of doing range queries. But overall, these two kinds of systems, the general NoSQL databases or key value stores here, and the hash-based key value services, they already provide very high performance compared to the old SQL databases. Comparing these two, the SQL and NoSQL, you can usually expect like 10 or 100 times faster access performance. But there is still a performance gap between in general, the NoSQL databases and the hash-based cache. One reason is that the key value cache, they never get into the disk. They always cache everything in the memory so that there's totally no I/O. But this is not the only reason. Another reason is that like the index performance, that what we are going to talk about in the next few slides. So in the NoSQL databases, such as this LMDB, is like a memory mapped B+ tree. So this tree maintains the keys in their alphabetical order, but it also caches everything in the memory. So if you think about the I/O cost, it's almost zero for this LMDB and compared with the key value caches. But the actual performance it can reach, or the queries per second it can make, is still like 10 times slower, at least 10 times slower than the key value cache. The performance gap between these two kind of systems is mainly about the index performance. So because when we are searching in an ordered index, if we want to keep keys in order, there is an extra overhead on the index data structure. So the goal of this work is to bridge the gap between these two kinds of systems, and we want to find a way to improve the ordered indexes so that any databases that wants to provide range query can provide a much higher performance, and that can be very close to a hash-based key value index. So a little bit about the history. So B+ tree has been the default index data structure for databases. If you look at the old databases from those big companies, from IBM, Oracle, those databases, they all have different interface, different names. But internally, they almost always use a B+ tree to index data. So those systems were designed when disks are the main kind of storage. So they don't have flash at the time. They only have disks, and then that was the main memory on top of it, right? So the disk I/O was the dominant bottleneck of the system. And in those systems, optimizations for performance always go to one direction, that is to minimize the disk I/O. So in other words, you could build very complicated indexes or whatever the metadata you want in the memory, and you can do a lot of computation in the memory, such as scheduling the I/O and do some use some heuristics to facilitate prefetching or whatever the things you do in the memory is going to be relatively faster than the disk I/O. So if you can spend maybe millions of CPU cycles to reduce one disk I/O, then your system will still go faster because the I/O was so slow on the spinning disks. And so for this reason, the B plus tree uses a very high find out in its tree node. So the example you see here is B plus tree, but you only see like 3 entries or only 2 entries in each tree node. But in the real B plus tree, the tree node size is much larger. Sometimes it's several hundreds of entries in each node, and this tree will become very wide. So each node can have like 300 child nodes, and each of them will have like 300 child nodes. So if you are managing a very large data set using a B plus tree, I think I have, no, I don't have an example on this page. So if you have, say, 1 billion items in a B plus tree, but if you have a high find out, you only need like 3 or 4 levels of the tree. So the tree will be very shallow. You don't need to go multiple nodes to find the data. You only need to read a few nodes into the memory to find the target data. And in this example B tree, suppose the root node is not cached, but usually like the top, the root node and maybe the first 2 levels of the tree nodes can be cached in the memory, and you need to use this I/O to retrieve some leaf nodes when you are doing the search. The number of I/Os you have on the B tree is a very small number. It's almost a constant number, such as 3 I/Os for a very large B tree. And obviously, the last I/O you make is at a leaf node, and this leaf node leads you to the target data. So this B plus tree has been working very well on the traditional storage stack with memory and disk. And like there has been like very little complaint about the performance of this, because like once we get to the disk, there's no different choices you can make on improving the performance. But the things has changed. Like if we are going to use the B plus tree to manage data in the main memory. In the main memory, the access cost is no longer in the node unit, right? Originally, like if you access a disk, you can directly read a large node into the memory, and there's pretty much nothing you can improve. But if you are accessing a huge B plus tree in the main memory, you're going to do binary search on those tree nodes to find which one is the child node I should go, and you go to the next node and you do another binary search. So a lot of binary searches here in the main memory will trigger a lot of different cache memory accesses, and it will lead a lot of cache misses for the search. So if you imagine like we have 1 billion keys indexed by a B plus tree, you need to do at least 30 key comparisons. And those key comparisons, like if you're using string keys, like using the emails as the keys, you're going to have pointers and indirections, a lot of complexities. So it easily goes up to like 50 or even 100 cache misses for one search. And at the end, when you reach a target entry in the leaf node, you may only need 1 or maybe 2 or 3 cache misses for the data access. So compare these two numbers, you will see that if we are developing an in-memory a key value index, the search cost can be much higher than the real access to the target data. So this work mainly reduced this number by introducing a new index data structure. So this is a very simplified example of B plus tree. It only has 2 levels, but this is sufficient to explain the main idea behind this. So we artificially divide the B plus tree's data structure into 2 parts. The top parts, we call it MetaTree, but this is just a term like we want to use in the paper to refer to this part. But you can consider like this part contains some metadata that leads your search to a specific leaf node. And on this second partition in the blue dashed circle, it contains all the leaf nodes of the tree. And those leaf nodes contains the real data in the system. So the purpose of the MetaTree is to facilitate the search. And once you enter the leaf node, the job is very simplified. You just find an entry there. And the cost of searching for the entry is like constant. So we want to compare these two parts here. To summarize, the search in the internal nodes, right? In this example, we only have one level at this in this root node, and then it's immediately the leaf node. But in the real system, it can have multiple levels here. And the search cost in this metadata component is O log n, because why is O log n? Because every time when we do a binary search, you rule out half of the potential key values in the system. So it's always bisecting when you are searching this component. So the cost is O log n. And when you are doing insertions and removals, you also need to handle merge, split, and rebalance, all kinds of complexities here. So this component has a lot of challenges on the design and the implementation. But when we are looking at the leaf level, all the leaf nodes here, things becomes very simple here. So every time the search leads you to a leaf node, you just do a quick binary search on the leaf node and you can find the keys here. And we can also do some optimizations in a leaf node, such as we order the key in hash order or some other order so that you can do point search much faster. But that details are a little bit out of the topic here. But you can see that once we enter the leaf node, things becomes constant. But when we are looking at the top components here, it's more complicated. So the first attempt we made on this data structure is we want to keep the leaf level. Oh, sorry, I forgot one thing. I forgot to mention one thing. That is, once you reach the leaf node, right? If you are going to perform a range search, such as return all the keys starting with J, or returning like the next 5 keys starting with some key, the range query on this structure is very efficient. You just scan this list and you can quickly get all the things you need with almost no cost on this process. The only thing that is expensive is on the search path. Okay, so the first attempt we made was trying to replace this search data structure with something else. And in particular, we want to replace it with something that is not bounded to the number of keys in the store, because the previous structure is based on O log n search cost. If you have a large store, this lookup cost will just increase with the store size. Okay, so what we do, okay, this slide is a summary of what we do in the next few ones, but I think I can skip this quickly. So how can we speed up the search on this upper component, right? Suppose we are keeping these leaf nodes unchanged in the new design. Can we replace it with a hash table? So this replacement will immediately make point lookups very fast. If you have a hash table here, you can almost use only one like memory comparison to check the keys and find where it is. This is a good story if you only use point search. But if you're going to use range queries, there will be a problem, because hash tables does not support range queries at all. Suppose you want to find like what is the first key that starts with a J here. How can you do the search? You cannot do it on a hash table because the keys are not ordered. And if you have a J, if you search on the hash table with the J, it will return nothing to you. You will not know like where is the start of this key. So immediately we know that hash table cannot be used for this purpose. And there are also other works that propose to use a hash table and a tree at the same time. So you index both things at the same time, and you can do point search very quickly with the hash table. And if you are going to do the range search, you're going to use the B+ tree. because you have two data structures that are indexing the same data set. But there are several problems. To name a few, that if you're going to do insertions or deletions, you're going to modify two data structures. That is like 2 times or almost 2 times more expensive than before. And we also need to double the space usage of the metadata. You need to create 2 data structures in the main memory. And also, this is the most challenging one. Suppose you have enough time and space, maintaining consistency between these 2 structures is extremely difficult, especially if you allow concurrent access to the system. How can you like transactionally update something in both the indexes? This is almost impossible in a lot of scenarios. So we actually look at a totally different data structure. That is a prefix tree. So the prefix tree, different from a binary tree or a B+ tree, is that prefix tree is a content addressable data structure. They use the keys to navigate on the structure. So where is the key totally depends on the key's content. So here is the word speed, S-P-E-E-D. The location of this key and or the relative location like between the seed and the speed, these 2 keys here are totally dependent on the key's prefix. And it's impossible that you move this key into another location, no matter what is the order you created this key, such as you insert the keys in the order or in the reverse order. It's always going to give you the same structure on the prefix tree. And if we just use a prefix tree to index a large data set, the lookup cost is bounded to the length, or is approximately the length of the key, because you need to traverse down to this chain of nodes to find the target. There are some optimizations to this data structure, such as the path compression. Like if you only have one branch here, starting from this P, you can like do some compression to make this path shorter. But those kind of optimizations are highly dependent on the data set. If you have data sets that does not share a lot of like long common prefixes, they are going to create a lot of branches in this prefix data structure, even though it's not O log n, but this L could be huge. Like if you have key sizes of 20 to 40, you can easily have like 20 nodes to traverse on this list. Sorry. So, and also another issue is the high space overhead. Because in this prefix tree, each node you need to allocate a fixed node size. I think in another paper they propose to use a variable size nodes here. But overall, the memory complexity and the space consumption for prefix tree is very huge, and simply because it requires a lot of nodes here in the data structure. So we have mentioned the 3 kinds of data structures so far: the B+ tree, the prefix tree, and also the hash tables. Their cons and pros has been discussed. You see that none of them is a perfect solution for like a very fast ordered index data structure. The problem of them, like the B+ tree has the high lookup cost. Prefix tree also has high lookup cost. They are not small enough. Like in a prefix, in a large data set, like both of these 2 indexes, they can use at least maybe 20 or 30 random memory accesses and also key comparisons on its search path. And for hash table, it does not support range queries. So that's something we cannot consider. But what I'm going to show next is that we can actually leverage the advantages of these few data structures, and we compose like a more sophisticated data structure that can achieve a much higher lookup efficiency in the real systems. So let's look at this B+ tree structure again. So we want to replace this structure with a prefix tree so that it's no longer binded to the log n cost. Because whatever the optimization we do here, if we still have a log n cost, we are not going to make much improvements. So the first attempt we made was to replace it with a prefix tree. Even though the advantage of doing this is not obvious, we are going to review this later. But right now, at least if we use the prefix tree here, we already get rid of the complexity of O log n. So suppose we use a prefix tree here to index all the keys here, and those keys maintained in this prefix tree are determined by the keys between like each two consecutive nodes. For example, this one. So the difference between these two nodes is that this node starts with an AU, and the previous nodes, the largest key, starts with an AN. So that if we store AU here, that means if your key is smaller than AU in the alphabetic order, such as AN or AB, it will go to the left node. And if the key is equal or larger than this one, such as Austin with AU, or other words starting with even larger, alphabetically larger letters, it will go to the right of this key. So we can, like very intuitively, we can use a prefix tree to index all the leaf nodes in this data structure. And this prefix tree is a sparse index. It's not a full index of the key value data set. It's a sparse index. If each leaf node here has like many keys, like 100 keys, the space cost of this prefix tree is very small. No matter how you waste the space here, you see that every node here is just 2 or 3 small letters, but each key in this prefix tree can index a lot of a large number of key values in each node. So using this prefix tree as a sparse index, we already avoid the space problem of a prefix tree. And then how do we perform search in this prefix tree? So suppose we are looking at some key that matches the prefix in this data structure, then such as James. James, if you just search on this path, you will find JAM. And if you already have a full match at the leaf node here in this red color, then you can directly find the keys in this node. This is the most simplified case. But there are several other like not that intuitive scenarios, such as if you're looking for Denise, right? The Denise belongs to this node, and all the keys are ordered in their letters, so it's definitely here. But how can you do the search? Because the letter D, the first letter, is not in this sparse index. It's supposed to be between this A and J, but we don't have this node here. So what we do in this data structure is, okay, if this node, this missing node, is between two things, we know that it must belong to the child node of the left branch you see here. So it must belong to the node belong to the left branch of this left sibling of this missing key. And we can go down to this node using two paths. Either ways, they are identical. If you go from the left path, you directly go down and you find the node. Or if you can go from the right path, and if you consider this is a subtree, that is like you are going from the leftmost path of its right subtree. So starting from this J, you go from its leftmost path, and you also need to jump one step left to this node. So either way, it's very easy to tell from the figure like where you are going to do, where you're going to go. And once you reach this node, the search is almost complete. You just need to do something in this node. And before I explain like the complexity and how does this improve, let's use a few other examples to explain that the search on this is always like straightforward and easy. So if we are looking for a key that does not is not between like two branches in this data structure, the rule is also simple. Like as long as you can find one path.
Sorry, I have a question. I mean, in this, you obviously have, if there is a lot of skew in the data, right? Right now, your keys are very randomly distributed.
Yes.
But if you have a lot of skew, then you have a lot of paths which are just beginning with AU, right?
Yes. Yes.
So yeah, you would have the same problem then, which you are trying to eliminate, which is the order log n problem. So I wonder how you are solving that.
Yeah, exactly. I will after I explain the search on this data structure, I will explain how do we improve this to make the search much faster. So yes, that was a good question. So if you have a lot of words with AU here, you're going to have a lot of more branches here, and the depth of this prefix tree will be much larger. Like you need to go down like 20 levels to reach a leaf node. And so I think maybe I can skip those examples because they are very intuitive. Like if you're searching for Julian and you don't have a right path to use, but you still have one path here. So it can be proved that you always has a path that leads you to the correct leaf node. And also searching for a non-existing key in this data structure is also very straightforward. But I think I can skip this part to the next one. So yeah, this is a problem. So the search cost on this prefix tree is OL. Then if you have a very long search path here, the search is not going to improve at all. This is not what we are like, it's not our destination on this work. So what we are actually do next step is to improve the lookup cost and asymptotically. That means we are not going to have this OL cost. We actually has O log L cost, but I didn't show this target on this slide. So the purpose of this search, not the purpose, is the essence of this search is to do some prefix matching. Either for the J or the D, we are just going to find the longest prefix match on this prefix tree. As long as we find the longest prefix match, and we can start from that location to reach a leaf node. And so there are two phases. The first one is longest prefix match. The second phase is to reach a leaf node using a particular path you can see here. So we are going to optimize these two steps separately, but in total, it gives us a lower search complexity. So, so there was research done like 20 years ago. They proposed a way to improve the longest prefix match using the binary search on prefix length. So that can improve the complexity of this from OL to O log L. And we can also record the leftmost and rightmost pointers in some nodes so that we don't need to really travel through this path. If we want to find the leftmost node of J, we just need to catch the pointer at this node, so it can directly lead to a leaf node. So these two parts will be optimized in this way, and in total, if we have a relatively small L, and the L is like, suppose it's 100, it's very conservative, right? 100 is a very long key, and the log L is only like 6 or 7. It's a very, very small cost. And in practice, the search cost of this is usually only 5 to 6, even with a large data set. So I'm going to give an example of doing binary search on prefix length. So suppose there is an anchor key. The anchor key is a key in the prefix tree. And if you want to find longest prefix match for the key, this is the search key Alexandria, you see that the last few letters are different. Actually, we don't need to compare the letters one by one because that is a tree. Every letter you compare leads to one memory access. So what we do is we add all the prefixes of this anchor key into a hash table. And we can directly probe on this hash table using an arbitrary length of the search key, such as we don't first search A, we directly search this prefix with 5 letters. We see that we have the Alexa, this word in this hash table. And then if it exists, we directly move forward and we add a few letters to it. So when the length is 7, it still exists in the hash table until we find a mismatch, because this R is different from this E in this in the keys in the hash table. So you are not going to find a match. But now you know that since this does not exist, but this exists, the longest prefix match is this is this prefix with 7 letters. So if you have this hash table and you only need to do like log L number of comparisons to find the longest prefix match, you don't really need to go down the path to find the match. Instead, you use the hash table to do this. So this figure here is a little bit into the details, but what we show here in this example is like we just encode this prefix tree in a hash table. This hash table has a lot of entries. These words here are the corresponding prefix of each anchor keys, and those letters in this green box represent like what are the child nodes you have. It's actually encoded using a bitmap, so it's very space efficient, such as this one. So this J, it has 2 child nodes. One is A and one is O. So you see that J has AO here. So using this hash table, we can directly use the binary search on prefix length to find the longest prefix match. And after the prefix match, we are going to use these numbers in the yellow boxes to reach a leaf node. So I'm going to show an example here. So suppose we are looking for Jacob. Jacob is here, but Jacob is nothing in this index. So when we are searching for the Jacob, we first search for a prefix such as JA, and JA exists here. And if this exists, we are going to increase the length. So add a letter here, C. So the length of the length 2 and 3 here is determined by the binary search, the size of the prefix. So C does not exist in this table. So we are going to come back to this JA, the last, the longest prefix match we find before, and to see that what are its siblings. So the C does not have, check, it does not have a left sibling. This JA, yeah, so this JA, at this JA, the A does not have a left sibling because the Jacob, the C is supposed to be here. It's supposed to be at the left of M, but there's no other nodes left to, such as AA or AB. So it only has a right sibling. So following the rule here, we are going to go down to this path and move 1 node left to this node. So we first go to the JAM node. The JAM is supposed to be the 3rd node here. And we are going to go 1 step left. So this will be the target node. And you actually see the word Jacob here. So this whole like pseudocode process might be a little bit confusing, but I think the key point is just like when you want to find the longest prefix match, it can be done by O log L time. And when you want to reach to a leaf node, you directly use a cat pointer here. You don't need to traverse on the tree. So the traversal on the prefix tree is totally eliminated in this search process. I'm not going to go through these details in the future. How many minutes do I still have? I think it's already 45, but I think I can quickly.
15, around 15 minutes, yeah.
15 minutes. Okay, thank you. So yeah. Okay, so the cost of this longest prefix match plus the cached pointer allows us to find the target leaf node without actually traversing on the tree. And we actually reach an, sorry, those are the details of the work. So the comparison can be seen on this table. So with this new data structure, like a hash table index prefix tree, we can achieve O log L search cost. We can directly reach a leaf node. And because the prefix tree or the hash table is like there is only a few keys for one large leaf node, the space cost for the metadata is actually very small. We are not going to create a full index for everything. And also it allows efficient range operations. That means no matter your key, your search key exists or not exist, non-exist in this data structure, we are always going to find like the smallest one that is greater or equal to the target key and do the range scanning on the list of leaf nodes. So this data structure is a fully functional range search or ordered index data structure, and it can perform the search at a much lower cost than the B+ tree and prefix tree. For comparison here, like if you have 1 billion keys and you have a relatively long key length, such as 100 letters. So in the B+ tree, you need 30 key comparisons. In the prefix tree, you need somewhere like close to maybe 50 or 100, depending on the data set. You need to traverse on a lot of nodes. But in this wormhole, you can do the binary search to find the longest prefix match and use one integer dereference to find the leaf node. So that cost is constantly below 10, even though you have a very like adversarial scenario, like you only need to do like 5 to 7 hash table search in this data structure. And also there are a few optimizations we have done on this. First is about the search optimizations. First, when we are searching on the hash tables, like each hash table lookup will require like computing the hash of the prefix, and also needs to do a key comparison to make sure that this key is really there. So this can be a very high cost if you do key comparisons. Like if you're going to do a prefix match for 5 times, you're going to do 5 key comparisons. Those are very expensive. So our observation here is that every time if a prefix match returns true, you're going to increase the prefix length until you find the prefix match. So in this process, we can actually avoid the string comparison to make sure that this Alexa is really the Alexa you are looking for. So when you are searching on the hash table, you just compute the hash and use the hash to find some matched entries there. This is not very intuitive because it involves a little bit of hash table design. But here, the core point is that when you are doing this binary search, we do not do key comparisons for these first few matches. Only when we find a mismatch, we are going to, such as we find that this Alexander with R, this string does not has a match, we are going to double check that this previous one is really a good match. If this is not this is a real match, then it means we already find the longest prefix match. We no longer need to compare the prefixes of this one, because if this one exists, the previous ones must exist. But if this prefix does not really exist, so that means the hash probing returned a false positive. It tells you that I have this prefix, but when you compare the key, you don't really find the prefix. Then you need to restart the search, like fall back to the old fashion. You need to do full key comparison for all the prefixes. That is more expensive, but depending on the false positive rate of the hash comparisons, you really need to do that. So in our implementation, we use 2 bytes as the hash in this hash table. Only in once in 10,000 times you need to do like a full key comparison search. So that is almost a negligible cost. So so we after the optimization we use, we can achieve like only 1 cache miss to find the longest prefix match, and to compare the last key to confirm this match. So in practice, we only need to trigger like 2 or 3 cache misses to finish this entire longest prefix match. That was, I think, where I didn't show the numbers in this page. So the entire hash table, the metadata we need to access, like if you have 1 billion keys, we only need like hash table of 50 megabytes. So that 50 megabytes can be mostly memory last level cache resident. They can be found in the L3 cache, and the search does not really need to go to the memory. That's why we need this very low cache miss rate here. And this is one optimization. And another one is, okay, sorry, this page was to explain the previous example. And another thing I want to briefly discuss, but I will not get into the details in the next 2 slides. So in these slides, we explain how do we maintain concurrency in the wormhole data structure. So we use reader-writer lock for each leaf node. So this is very intuitive. Like if you have multiple threads or clients, they are accessing different locations in this tree, they don't block each other. Like those are few readers, they can share the read this node, and this writer, it can operate on this node. There will be like contention, like if multiple writers go to one node, they need to grab the lock and do the insertion or deletion sequentially. But overall, like if your workload is not concentrated on a few points, the scalability of this read-write efficiency is very good. And it's as readers and writers. And also, we need to like split and merge some nodes when we like inserting too many keys in one node. So we use structure named we use the RCU mechanism, that is the read copy update mechanism. But the real implementation is very complicated. But the but a few key points is that we use 2 data structures here, and every time the readers will use one, and the writers that will do a split or merge on this leaf list will use another one. So these 2 data structures, they do not block each other. And once the splitter, we call the thread that splits a node a splitter. When the splitter updates this node, it's going to let the readers to go from this path, and the splitter will update these 2 nodes. So it maintains like 2 versions in the memory and allows the readers and writers to always access some node without blocking. But the details of this part, I think I should skip on today's talk. So I'm sorry, I'm going to skip those animations. So a few words about the performance evaluation. So we test this data structure with several like realistic keys in the real world, such as the Amazon's review metadata. There are the customer ID, the product ID, and there might be a like timestamp for those reviews. You see this entire key is very long. It's not like a small integer key. If you use a prefix tree for this, you're going to access a lot of nodes. Then also this mem tracker, it also contains a lot of URLs. Those URLs can be very long. And we use several data sets, and this is a machine's configuration. and we compare our work with several other data structures, including the ordered indexes and also the cuckoo hash table. It's a very fast hash table. Oh, I think I didn't put the result for the hash table here. So let's just look at the lookup performance. So the wormhole's lookup performance is on the blue bar. The y-axis is the throughput. So the higher, the better. The x, each cluster here is one data set. So you'll see with different key, these numbers here represent the key size. And the first two are the Amazon IDs, and the third one is the memory tracker URLs. They show different performance characteristics, but overall, the wormhole can achieve a very significant improvement for all the scenarios. And because this is simply because it requires less computation overhead and less catch misses. So for the skip list and B plus tree, they are considered similar data structures. This MetaTree is a very popular data structure that was introduced in 2012. This MetaTree combines the B plus tree and the prefix tree, but its prefix tree is still like a regular prefix tree. So searching in this MetaTree is very close to the cost of a B plus tree, but it optimizes the access it optimizes accesses using some SIMD instructions. The SIMD instructions can do comparisons, like it can compare 15 keys in one instruction. So that can gain some performance boost using those advanced instructions. But overall, the wormhole has lower asymptotic cost, and in practice, it also requires less CPU cycles and catch misses. So it achieves very significant improvement, especially when we are searching for very long keys. You see that the MetaTree has a very low performance here. Compared to previous results with very long keys, the wormhole can still outperform other systems by about 3 times or more. And for the space cost, because we are using whatever it is some sparse index. That means for each leaf node with hundreds of keys, we only record like one set of prefixes in the data structure. So you see the space cost of wormhole in the blue area is very close to the B plus tree and skip list, those like regular data structures. And this MetaTree, it has the problem of prefix tree because it's a combination of prefix tree and B plus tree. And you see that its space consumption is much higher than the other stores, except this one. In this one, we have very, very short keys, so it does not have the space problem. That's all for my presentation, and I hope we still have time for some questions if you have any.
Hi, I'm James. I had a question for you. So what I don't quite get is computing the hash codes, right? So ultimately, if you're computing the hash code of a long string, yeah, that's going to be linear time, right? So I don't see how you're getting away with that.
Yeah, there was, so I think there was an optimization, but was not mentioned in this slide. So let me use this example. So we are using the CRC32 hashing. So that hash algorithm allows you to do incremental hash. Say if you already calculate the hash of this Alexa, this 5-letter prefix, if you want to calculate the hash for a longer prefix, you only need to like add the last 2 letters into the previous hash value. So
yeah, that I understand. But yeah, at the end of the day, though, right? It's still linear time. If you have a string that's 1,000 characters, you've got to go through them all. No. Yes.
So I think there are 2 things about this point. One is this: if you are talking about the complexity of scanning the key, that is definitely OL. So we are looking at the search cost. So that was we say that is O log L, but that O log L is the number of probes on a hash table. Because we use the assumption that searching on a hash table is O1. But I think, yes, there might be some conceptual mismatch here. Because when we are talking about hash tables, we should not say the hash table search cost is OL, simply because we need to calculate the hash of a key.
Well, it can be pre-computed, right? But in general, right, you're going to have to deal with it. But I mean, ultimately, what you care about, I guess, are the experimental numbers, right? So if the experiments bear out that it's not an issue, then it's not an issue, and that seems to be the case. Is that right?
Yeah, I agree with you that if you think about the number of bytes you need to scan through the hash, then it might not be the O log L, and but I think it's not an issue in practice because in this sparse index. Let me scroll back a little bit. Yeah, in this sparse index, we are going to use like common prefix between this, like Andrew and Austin. Use a common prefix of them, and if they have if their common prefix is just A, right? So we just use A plus one letter as the anchor key. So in practice, in those systems, the length of those prefixes are very short. So you're going to find a prefix match without like going through like 1,000 letters. You usually, like even if you insert very long keys such as that URL dataset, when we like inspect the generated the wormhole data structure, we find that the prefixes are just maybe 15, 20 letters there. And even though the prefixes, the URLs are more than 100 letters. So in practice, scanning the hash prefix is not a problem. And this, we need to, this is because the use of a sparse index. So even though you have very long keys here, the sparse index will still give you some much shorter prefixes here. And I think we mentioned that in the paper that how do we find the cut point like between these two, right? If you cut like between Julie and Justin, like you may have a longer prefix. But if you cut somewhere else, you can have a shorter prefix. So that is still an open question.
All right, thank you. I enjoyed the talk.
Yeah, thank you.
You mentioned in one of your first slides that that NoSQL databases are like 100 to 1,000 times faster than regular SQL databases. I'm having trouble understanding how you got that, because surely if they're both using indexes, you would have similar lookup costs, right?
So for the NoSQL databases, because I think I used a relatively vague word here, that is NoSQL databases. There are so many different kinds of them. But I actually emphasize like one kind of them that are the most simplified key value databases. So the key value databases is just the index lookup, and it can go to this performance. And for the SQL databases, in this MySQL, Oracle, there are a lot of cost on the locking and doing I/O, and also the index search, and it also needs to do a lot of other things. But I think I don't have a very detailed list of why it can only go to like 1K to 100K. But those databases, I think it usually involves I/Os. But for point search, like if they are using the same data structure, if they organize the B tree in the memory, I believe, okay, they can achieve this. But those databases, they are like serving like 100 different purposes. They are not
actually that I also have a little concern about the motivation over here. So and maybe that's something that might be useful to look into. So for one, like like LevelDB, for instance, does not use B plus trees. So most NoSQL databases use LSM trees. right? So to say that this is a thing for NoSQL databases is counterintuitive, because none of them use B plus trees. I mean, B plus trees are in relational databases, but not in NoSQL databases. And I mean, it's known that B plus trees are not write optimized. So that's why they don't exist in NoSQL databases. So that I see as a, I mean, now to the fundamental problem of improving the efficiency of B plus tree for primarily read-only loads, yeah, one can introduce some sort of caching or extra storage in some senses, and which you are doing through the hash table specification. So there I wondered that, instead of a hash table, if you actually use a Bloom filter, for instance, which is actually represents the distribution of the values without taking, what James was mentioning earlier, the hashing cost of each particular key that you are hashing, I think you would be better off. But that's, again, you have to sort of experiment that. Because normally these memories for summary structures is maintained through Bloom filters, because they have better they capture the probabilistic distribution amongst the keys in more succinct space. So yeah, that is something I feel that you can look into. Yeah, but definitely the skip lists will be doing better than keeping all the values.
Yeah, I think the examples here might be a little bit diluted. So I think for the SQL database, I'm not saying that it's slow because it uses B plus tree. I think it's more about concurrency control and I/O. But yeah, but for the NoSQL database, I think I should maybe change the terms here. Like for the LMDB, it's essentially just a very plain B plus tree. And for B plus tree, it's already like most read friendly. So everything is already well sorted. You search in a B plus tree, it has the O log n cost. And if we are talking about level DB, they are using the LSM trees. So in the LSM trees, you are like stacking multiple trees in a database, and searching in a level DB can be much slower than a B plus tree, or at least it's never faster than a plain B plus tree. So if we are looking at the lookup performance of those systems, you can consider that the B plus tree based key value store represents the best performance of any like ordered databases. So that is the best we can get. That is a plain B plus tree. And for higher performance, we have to resort to hash tables. So without using hash tables or any kind of those hash-based caching, you cannot increase the performance to the next level. So that is the main point here. That is the performance of ordered databases are kept by the ordered indexes. Sure. So we are going to improve this part. Yeah. I think the examples here are not like very not very good. I should improve this later.
Any other questions? Tim, Jordan, if you have.
Yeah, just more of a comment. As a heavy user of Amazon S3, they support prefix searches, but not range searches. So I would.
So handling prefix range searches is there are a lot of techniques like tricks you can optimize in the data structure. We are also did some research recently about that. So the most challenging part is about open range queries. That is like you give it a key, like ABC, and you want to start scanning from this key to the other keys, and you don't know where to end the search. It depends on the programmer's logic. So that scenario is most challenging to address. But for like prefix search, like if you want to retrieve all the keys starting with one prefix, there are some work called range filters. I think there have been 2 papers. One is called Surf. The other is called Rosetta. These 2 papers are on VLDB in these recent 2 years. They target those problems about mostly about close range query. And based on what I learned from those papers, like if you are handling some stem prefix searches, that is there are some space like for you to like easily improve. But in general, the range search is still an open problem, and like no one knows how to like improve all the range searches in those systems.
I see. So you're,
go ahead, Jordan.
Yeah, so the solution you presented here would not help with kind of the open-ended range searches.
Oh, the limitation of this work is that it's talking about memory only databases. That means you have the index in memory, and you may not have the data in memory, but the index is already in memory. So we are talking about the search complexity. So if you're doing a range query on this wormhole, the result is near optimal because you already have everything on a linked list. You just scan the list, you find the next few keys. No matter you are looking for like same prefix keys, or you're searching for keys like the first 100 keys starting from starting from a specific key. The wormhole can do this very efficiently. But if you cannot hold this entire index in the memory, like if you need to swap it out into disk, then the overhead is another story, but it's not part of the research.
Gotcha. Thanks.
Thank you.
Right. Is this limited to even strings, like, or do you assume that it could be an integer or a real number, the key?
Yeah, I also got these questions before. So for integers, you can also convert this integer into like a binary representation. Like if it's a 64-bit integer, it's just a key of 8 bytes. So it's there's no compatibility issue with integers and strings. It can handle all kind of keys. But for integers, usually they are very short. So the improvement for integers is kind of reduced. Yeah. If we look at the very end of this, you will see that, oh, sorry. So if we are looking at the 8 bytes keys, the improvement is reduced compared to the long string keys. With long string keys, if we compare with the MetaTree, we can improve like more than 6 times. But with the short keys, the improvement is only like 2 times. So if you are not using long keys or like variable length keys, the advantage of wormhole is kind of reduced.
Okay. Other questions? Okay. Well, thank you so much, Xingbo, for this. Very interesting to hear about this. And yeah, thank you again.
Yeah, thank you for inviting me to this talk. I really enjoyed it. Yeah, thank you everyone for attending this talk.
Yes, yes. Bye-bye. Thanks.
Yeah, bye-bye.